To understand the furnace operation success, we must start with the voidage. The ratio of empty space between the solid particle to the total volume of burden. Think of voidage as the room available for furnace gases to flow through as they ascend from the tuyas. Large uniform material like metallurgical coke create high voidage and act as critical gas distributor. However, fines smaller than 5 mm act as a gap fillers that settle into these spaces, effectively clogging the furnace. In regions like Odisha and Jharkhand, the shift towards Goethite richer has made managing these voids more complex due to their high chemically combined water content. Now, resistance to gas flow is not linear. It follows the Aragovan equation where resistance is proportional to term 1 minus epsilon whole divided by epsilon to the power 3, because voidage, that is epsilon, is cubed in the denominator. Any small decrease in a space leads to an exponential rise in resistance. For example, in a healthy furnace with a 45% voids, the resistance factor is roughly 6.0. If fines reduce that voidage to 30%, the resistance factor jumps to 26. This means a mere 15% loss in total space makes the furnace nearly 4 times harder to drive. Now, this relationship is quantified by loss of ignition, which measure the mass of volatile like hydroxyl group or CO2 liberated during heating. Because of the cubic maths we just discussed, even a teeny amount of fines causes a massive spike in pressure. A 5% increase in fines can trigger 20 to 30% rise in pressure drop across the furnace stack. Conversely, removing just 1% fines from a charge can increase our blast furnace's blast intake by 1.3% because the gas move so much more freely. High pressure from the fines create a upward force that support the burden weight, leading to operational nightmares like hanging and sleeping. Furthermore, the liberation of volatiles from a high LOI material is endothermic, extracting sensible heat from the ascending gases and quenching the upper shaft. Now, high LOI lumpur are particularly dangerous because they generate fines inside the furnace through a process called thermal bursting or decrepitation. These ore contain chemically bound hydroxyl group that transform into steam instantly when heating hot gases between 250 degrees centigrade to 400 degrees centigrade. If this steam cannot escape the mineral lattice quickly enough, the internal pressure exceeds the mechanical strength of ore and shatter the lump into fragment. While porous ores sometimes allow this steam to escape through relief valves, dense martite goethite ore often suffer severe shattering, clogging voids that were clear at the stockhouse. Now, coming to the porosity paradox and the operator's strategy. Interestingly, high LOI ores often have a porosity paradox. They actually show better reducibility than dense hematite. This is because the escape of combined water leaves a microchannel network that facilitate faster gas diffusion. To exploit these while maintaining stability, operator must use a center working charging pattern. By creating a coke chimney at center, you ensure at least one area has maximum voidage for gas to escape, bypassing the fines generated in the periphery. We also enforce a strict screening. Fines loading greater than 7% sampled at a furnace leads to serious operational failure. Now, coming to the mastering that's high LOI burden, we must integrate proactive slag engineering and thermal control also. High alumina load associated with the goethite ore must be balanced by increasing MgO content to maintain slag fluidity and hearth drainage. Continuous monitoring of delta P is your first warning that the voids are closing. By strategically selecting clamp ore based on metallurgical properties and decrepitation index, we can partially substitute sinter and pellet to reduce carbon emissions while maintaining a